Well, hey guys, this is part 2 of the video about bridging and paralleling amplifiers for more output power. So why do you want to parallel a chip amp for more power? Well, for example, if you're constrained with the chip amp's output current limit and you want to drive a lower impedance load with the given supply voltage you have, you'd have to parallel them. And in my example, I'm going to use the LM1875 because, and normally you'd want to step up to the higher chip amp, such as an LM3886, like I mentioned in the previous video. But I don't have any of those chips, and they don't plug into these breadboards easy due to their staggered pin spacing. So I really can't use them, and the LM1875 will work just fine for that purpose. Okay. Can you parallel a discrete amplifier? Well, sure. But why would you want to build a whole nother amplifier? What's normally done with discrete amplifiers is to add more output pairs in parallel. As long as your voltage gain stage and your driver transistors are up to it, the designer just all he has to do is add on more output pairs in parallel configuration to handle the heavier current. And with these high power amplifiers running, I don't know, 500, 800, even higher wattage, you'll see like 8 or more output pairs of transistors. And if you look into those old PA amps, you'll see a whole bunch of those TO3 type transistors in parallel. So that's what they're doing there. Think of it as a train pulling cars. You have one engine pulling a few amount of cars, perfectly capable of doing that. Now, I know sometimes I see short trains with more engines. That's probably because they're going to go pick up more cars, or they need that engine in use somewhere else. But generally speaking, one engine is plenty for a short train. If they're pulling a heavier load, you have to add more engines. Same case with the amplifier. If you're going to drive a lower impedance load that the chip can't handle, you can parallel them. It's kind of like adding another engine so you can handle that load. Okay, since I'm going to demo using the LM1875, we need to take a look at its capabilities as it stands. Well, through some measurements, I found that the LM1875 has a RMS maximum current output of 3 amps. So 3 amps RMS. So, do we need to parallel if it's driving an 8 ohm load? Well, let's take a look. Well, I measured up to 55.2 volts of supply, plus and minus, what would that be, 27.6, I guess. And our output voltage swing was 16.4. And our watts of output into the 8 ohm load was 33.62. And remember, we have 3 amps RMS to deal with, but we're only putting out 2. That gives us plenty of headroom with most speaker loads, because you have to remember speakers are a reactive load, and sometimes they will draw more than meets the eye here at this given situation. So the LM1875 is plenty capable of putting that kind of power into an 8 ohm load, and you still have plenty of headroom. Well, in lies the problem with 4 ohm loads. Normally you decrease the impedance so you can put more power into a load, but with our 3 amp limit, see what happens here. We come up, let's see, about the same output current, about 2 amps. Well, we're stuck around 30.65 volts. We're only putting about half the power, yet we used a 4 ohm load because we reached our limit. We're at 2 amps. Again, not 3 amps because we want to be able to drive a reactive load, so we give it headroom. So we're stuck here. I mean, I could keep going with a non-inductive resistor. And at 36 volts, I got 25 watts, but you know, we're getting close to our 3 amp limit. So yeah, 2 amps, 8 ohms, a lot of power. 2 amps, 4 ohms, about half the power. We're just limited. And if we even go down, let's look at 2 ohms. You can see here with a non-inductive resistor, I hit this limit here, and our output pretty much stopped. And at, well, I didn't get an exact 2 amp, but 2 ohm load, we only got 9 watts with a 18 volt supply. You know, that's plus and minus 9 volts. So yeah, the lower impedance load caused us problems because of our current limit. Now let's do some quick calculations here. Let's say I have an LM1875. We have a plus and minus 20 volt dual rail. In other words, 40 volt total supply. 8 ohm load connected to its output. And we'll figure that we lose a couple volts before clipping because of losses in the amplifier circuit in the real world and all that good stuff. So you have about 18 volts peak. So the RMS value of that would be 12.7. And with an 8 ohm load, we can get about 20 watts. And the current draw would be 1.6 amps. Well, that's no problem at all for the LM1875 because, again, its current limit is 3 amps. So what happens if we decide to connect a 4 ohm load? Well, negating the extra losses from the current, we'll be getting around 40 watts. Probably would drop to like 35 or 6 or something like that. But you look here, we're exceeding its current limit of 3 amps. Now we're putting 3.2 amps into the load. Its protection circuits would kick in and prevent that from happening, and our power would actually decrease even more. So this is where we can double up the output to handle that. Okay, so what I did here is I paralleled the amplifiers. Not to confuse you, it does kind of look like a bridge amp, but it's not. If you look carefully, it's a single-ended load. You know, the load's tied to ground and the other side tied to the outputs. Whereas the bridge, it was tied across the outputs. There was no ground connection. Another thing is the signal fed to the amplifier is both in phase. So, you know, with the bridge amp, this side was out of phase because we wanted to generate the difference voltage across the output stage for the, higher output power. So with each output stage handling half the current, we can now double up the amount of available current we have for our load. So in the case of the LM1875, we had 3 amps RMS. That now, with the 2 output stages, we get 6 amps RMS maximum. And I give like 2/3 headroom for reactive loads. So that now gives us 4 amps to work with. And in this case, we still have plenty of headroom. 3.2, that's about half of our 6 amps maximum. So, this will work. Alright, well, let's move over to the workbench and demonstrate this. Got a little ahead of myself. I need to show you a schematic. This is a complete amplifier. I'm not showing the supply rails and the decoupling capacitors on the supply, just to keep it simple. So to bridge these chip amps, you have to do a few things that are very important. Well, the output of these must be completely identical, because if this one's putting out a signal and this one's not, or it's significantly different, high current's going to flow between these amplifiers. You don't want that. You want to get your current into the load. So you have to make sure the gain of these two amplifiers are set exactly the same. So you have to make sure your feedback resistors, input biasing resistors, that is, are very close. So you want to use 1% tolerance resistors. Metal film. Of course, you should be using metal film on anything with amplification anyway, audio amplification. So all these marked with the asterisk must be 1% tolerance resistors. And this here is just the input RF filtering. So I just bring the inputs together here to the filter. So this circuit will be evenly, or this input signal would be evenly divided between the two amplifiers. And on the output, you notice there is a series resistor, a very low value, 0.1. Well, this helps in sharing. In the real world, these will never completely match an output signal. There's going to be a very small few millivolts difference in signal. So the beauty of this circuit, with each output having 0.1 ohm, so if there is a mismatch, this will limit the current, and it puts these two resistors in series. So it's between the amps, it's 0.2 ohms, and they're in parallel to the load, so it's 0.05 ohms in series with the load, because you can see they're paralleled. So it's very important to take these into consideration. So now move over to the bench. Alright, I reconfigured the amplifier from bridge mode for the last video, and now it's in parallel mode. And these are the current sharing resistors. Note, kind of a bad design. I have this output close to this input. I did ground one of these segments, hopefully isolating it a little bit, but it still could be a problem. And of course, I have the inputs connected together, so they're just two non-inverting amplifiers that are paralleled. Alright, turn on the power. Bring it. Uh-oh, not good. The light is glowing. Houston, we have a problem. Well, let me see what the problem is. And could be oscillation, I don't know. I'll get the scope involved here and see if I can fix it. Well, it looks like I have some problem solving to do. One thing you can do to make sure your amplifier is perfectly balanced is to simply connect a speaker across the channels like that. Because the signal should be identical, you should get practically nothing. Maybe the slightest bit because of imbalance. But if you hear some weird distortion or anything, you have a problem. That's what I'm getting here. So I have a speaker connected between the channels. I switched over to this power supply. Hear that? That horrible distortion between the channels. We have, it's not really the chips, I don't think. It's just the layout. You may not be able to solve it on this type of board, but we have to fix it. It could be just wiggling components, not making good contact. Aha, I found it. Wow, current shoots up when I wiggle this component. It's a weak ground causing distortion. When I pull it this way, it goes dead silent almost. So yeah, it's a grounding issue. I gotta get that fixed. Okay, I tried adding an extra bond wire for grounding, so it lowers the resistance for a better ground. I mean, these socket boards, you can only do so much. There's always going to be a few milliohms of resistance. And when I wiggle these, I still get a little bit of difference. But the output, I mean, the amplifier's cranked up to almost full power, and the difference in the signal, I don't know if you can hear that. Slightly, but it really should be almost zero, and there shouldn't be that distortion. I mean, there's always, in the real world, there's always residual distortion and difference, but I mean, the ground is what's causing it. It's just not a great layout on these boards. Might have to resort to soldering up a board. I really don't want to do that. Waste chips just for that. But I'll get this as good as I can and continue on with the experiment. Well, this is a fail. I cannot get this circuit to work. It's kind of interesting though, and I'll explain that in a moment. So had this circuit worked, how much power would I have gotten out of it? Well, again, with an 8 ohm load with a single amplifier at 50 volts, you know, that's plus minus 25 volt rails, I would have got 28.5 watts. So if I paralleled the amps, ran with 4 ohm loads, you know, they're splitting up the supply current, so you're not going to incur additional losses, except you will a little bit in these paralleling resistors here, current sharing resistors. So I've probably gotten around 55 watts of output. That's pretty good. Well, now off to the reason why this doesn't work. So what we have here are two amplifiers with their outputs connected together through a low impedance where high currents can travel. You know, one can be pulling positive, one can be pulling negative, and creating, you know, quite a bit of differential current. And we got this ground plane here on this board that links the amplifiers together, and the capacitors here connecting in the middle. I added some smaller ones as well to help, and kind of like a star ground for the load and the input and power. But still, we're still raising a differential current across these amplifiers. So what I have done, I connected the scope to this side of the ground near this amplifier, and the other side, you know, near this amplifier. So we're seeing what voltage drop is created across the ground plane. So let me, well, first let me show you here. I have a bulb limiter here, and that's a 60 watt bulb, and it it lights it up pretty darn bright. So look what's happening here. We're getting, this camera is just a pain when it comes to focus. So we're getting about 1 megahertz oscillation going on there. It's not stable, it's kind of jittery, but 1 megahertz and about 50 millivolts across the ground plane. I'll turn that off. So that is the fail. I'm just unable to use this board because, you know, if you have voltage raising across the ground plane here between your amplifiers, they're gonna oscillate. There's just nothing I can do about it on this board. What I would really have to do is, you know, put on a board where I can solder the connections and, you know, arrange these so I can have a better ground. That's where it'd be nice to have extra money. Yeah, maybe GoFundMe. I don't know. I really don't like to beg for money. But I just, you know, I don't want to waste components and stuff. Because, you know, I have to buy more components to replace the stuff I use with, and yeah, it's just not a good situation there. So yeah, unfortunately I just can't show you in a demonstration because of this, but hopefully you get the idea, and thanks for watching.